Okay, welcome back to the DOTS lectures. Sorry for that hiatus. Today we're going to continue on looking at these loose right modules of systems. So last time we saw this example of having these diagrams. They're just poking through in the back here. We have more machines of a certain sort defined by this so-called tangency. And we looked at how you got a module of these systems acted on the right by lenses. And today we're going to look at another class of examples here. Although we'll start with a very basic one and then generalize it, which are all under the purview of these things that we could call behavioral approaches to dynamical systems. So these are going to be modules of systems which follow Jan Willems' behavioral approach to control theory. And so we're going to give a module of systems that works like this. So zooming, tearing, and linking. And the idea is that we have a bunch of systems. So we'll put it here. So we have, say, systems, and a system lives in a little bubble. And poking out of that bubble are these little wires, and these little wires carry variables that make sense for the system. And if I have another system, right, and it has some wires coming out, then we can, and I'll maybe, call this X prime, Y prime, Z prime, whatever. Then we can link these two together like this via a link. And this, and maybe we can also link these two together. And maybe we can also link these two together. And then we can put the whole of this in a big bubble. And anything remaining we can just have poke out. And this is linking up the systems. And this is going to represent setting the variables equal here. And we're going to give the mathematics of this in a bit. In both of these systems. And so the idea of zooming is that if I started with this outer system, which we could call S1 composed, well, as we'll see, there's a composition pattern here. So there's this composition pattern that I'll draw below. This is the abstract composition pattern, C. And this is where you can write, S1 tensor S2 dot C, right? Using our sort of notation from up here, I hope. Using these kinds of left composites, there's our dots. So just as before. And so if we had a big system, which was this composite, then we could zoom in and see that it was actually composed of things like this, supposing it was. And then tearing is this idea that we look at each one of these S1 and S2 individually, and linking is what we just did. So these are the operations of Jan Willems' behavioral control theory, and we're going to see how they fit in with the double categorical approach we've been describing. So there's a very, very simple formulation here that will make increasingly more robust as we go on. And so Jan Willems has a very simple notion, you could say, so this is a very minimal notion of system. So a system is a set of possible behaviors. Here's what we call S. But of course, remember that we always need systems to have interfaces. So an interface is a set of possible behaviors of that interface. Set. So I in I, and then a system, and then of course we have to say with interface I is a set of possible behaviors together with a function, which I'll call E or ES, which exposes the interface behavior. So let me give an example of this. Consider a system which is a bucket of water. This the water has a certain height, h, and imagine we have little pipes at the bottom, little holes at the bottom, and there we can consider the pressure. Sorry, P1, P2, the pressure and the flow of water potentially coming through these pipes. Now, supposing that those pipes are available to be connected up to other buckets, right? We'll have that the I for this system, I will equal some functions, right? Some functions, we'll say here, it equals this P1, P2, F1, F2, and both of those are going to be functions of time. And the system here is going to be I together with H, which is also a function of time. Right? However, that's not enough. So maybe I'll give myself some more things to say. He'll be, so P1, P2, F1, F2 in I, comma H in R4. But there's also going to be some equations that relate these.
H is just
Sorry. Thank you. And there's also going to be some equations that relate these. Right? So maybe we have some equation that says, well, the height, the way the height changes depends on how much is flowing in and how much is flowing out. And so I'm not going to really care about the details here. I'm gonna just say that there's some equation governing the change of height, which maybe depends on the pressures, flows, and the flow is going to be depending on the height and the pressure. No, H, not H1, just H. Right? So in other words, we have a bunch of functions of time that are subject to equations, right? And then what is the projection? What is this exposed function? Well, we just expose, P1, P2, F1, and F2. So you see we have some variables here that are available for, coupling down the line. And we have some other variables which are internal to the system. And then we have some equations that govern, that tell us what of these actual values are possible for the system to achieve. So right here, it's a system of sort of like algebraic differential equations, right? Or differential algebraic equations. But like in principle, this could we could constrain S in any way. So in general, what you're going to have is something like S is some kind of subset of R to the N varying in time, and I is some subset of R to the, like, say, is there, maybe I'll make it nice and nice like this, N plus K to the R, and this is just N to the R, and we have just a projection here. And in general, that's what you're going to have. And very often the interface will not even be constrained. So that you can imagine that it's very possible that all of your variables are open for coupling, and all you know about the system is that actually some of those variables are constrained by equations defined by the system. So this is, again, an extremely minimal definition of system. And what I hope to show in the next few lectures is that this notion of system and its resulting system theory, its module of systems, is universal in a very precise mathematical sense amongst all these modules of systems. In a way that I think really justifies, post facto justifies Jan Willem's behavioral control theory. We'll see that behaviors of any kind of systems theory, as long as they are representable by morphisms of those system series, will give rise to Jan Willem styles behavioral things. But now, let me talk about how we couple these. So first of all, right, let me look at this. How would I actually write this? Well, I'm going to write this like this, S here, and then I'm going to poke out 4 wires because we have 4 exposed variables, P1, P2, P3, P4. So in this case, we're going to take this, we're going to say that the interface is just going to equal R to the N with some extra things. Okay. So this is how we would draw such a system. So now suppose we have 2 buckets. And then we pipe them together. We want to pipe them together. Right? Right. So now we have to look at how we will actually do that. Let's call this S1 and S2. They're both going to be copies of the same thing. So in other words, we have over here we have S1, and I'll actually give a little version of this. We'll draw these in. We could draw them as bubbles, but it also is nice to draw them as boxes, just having 4 things coming out of it, like this. S1, S2. And now we have to understand, like, what does it mean when we couple here? Well, in here, right, we note that if these are the same pipe, the pressures are equal. So we'll say P11 is equal to, or so P12, the second pressure of S1, is equal to the first pressure over there. And we know that their flows have to be opposite, right? If it's flowing out of one, it's flowing into the other. So we have F12 is equal to, plus F21 is equal to 0 is one way to say that. So we're going to write down that expression in terms of a diagram here. So first, I have to make sure I've labeled these. So P11, P12, F11, F12, P1, P21, P22, F21, F22. Okay, and then we can go and hook this up. So we're going to, first of all, we're going to connect these 2 together. But we're not going to put any more wires coming out of that because this pipe is already used. It's no longer available. P11 is still available. It's on the left, and so is F11. So I'll have that come out. Similarly, P22 goes straight out, and F22 goes straight out. And now we're left with these F21s here, which I'll put into a little plus, and then we'll say here a little zero. And I'll explain what that means, but the idea is that when you add those two together, you get zero. So this is the kind of picture we would write down. So let me express how we can turn that picture into an actual operation that's going to compose these things. So what do I mean by that? Well, first of all, like when I say that we have this system is given by taking those two systems and setting those equations, what I mean is that we take S1, right, which equals the set of F11, F12, P11, P12, and H1, subject to some equations. S2 is equal to F21, F22, P21, P22, H2. H2, subject to some equations. I'll call them maybe ec1 and ec2, just so I can refer to them again. I don't want to write them out. And we have these extra equations. So what do we do? First, as in all our things, we take their parallel product, which in this case is the Cartesian product. So we get S1 cross S2. And this corresponds to this intermediate little diagram here. You know, the very first thing we did when we drew this is we just put them together like this. So first we lay out the systems together, and then they have all four variables, right, available. So this, right, is equal to the set of wow, F11, F12, P11, P12, comma, F21, F22, P21, P22, comma, H1, H2, subject to equation 1 of the ones and equation 2 of the twos. Right? And then we take the actual composition law, right? W, which is out here, which corresponds to these two equations here, and we add those in. So now when we take this and we take this and we compose it with W, right? We will get S1 times S2 composed with W. And that is the same exact thing, but now we have ec1, ec2, and we have our two equations. P12 is equal to P21, and F12 plus F21 equals 0. That's all it means. It's sort of belaboring this a lot because we're going to do it abstractly now. But this is all it means. When you couple systems together, you just throw in some equations together. Okay. So let's take this diagram here, which I'm just going to copy. Because I want to emphasize, of course, that when I say like we take the diagram, I mean, it doesn't anymore refer to the inner parts. It's just that diagram. And what I want you to note here is that this diagram has a sort of nice combinatorial form, right? We have here, up here, we have four variables, right? We have a set, which is P11, P12, F11, F12, and then we disjoint union it with, or I'll use plus, I always use plus. We disjoint union it with the other set of variables, 21, P22, F21, F22, right? And then out here we have our remaining variables, P11, F11, P22, F22. And then in the middle, we have some of these junctions, right? So I'm going to name them J1, J2, J3, J4, J5, and J6. We'll look more closely at this in a bit. But So what we can see is that in here we have the set of junctions, J1, J2, J6. And what you can see is that the wires, I can actually see them as telling us how to give a functions like this, labeling each of the inner ports by which junction they connect to, and each of the outer ports by which junction they connect to. And then also, some of these junctions, specifically J6, we adorned with a relation symbol here, which I won't go into right now, but we can come back to in a bit. But this is the main thing, is that like F1 and F2, we interacted them, but the relation we put on them was not equality, but that they sum to 0. And so that's the only thing. We really, what we have for every junction is some relation of this appropriate arity from the left-hand side. But we'll come back to that later. It's much easier if you just equate things. Okay. So what does that mean? Okay, again, we have this big thing. So now, right, we have S1 times S2, right? Oh, one of the things to note, right, is note, of course, that none of these variables referred to the height. The height was determined internally. So we have our projections here, I1, I2. And then what we have over here is what I'll call, I3, which is equal to, the set of the variables P11, P11, F11, P21, P22, F22, right? And then we have our junctions. Now the junction set is equal to the set of all the inner variables, inner interface variables. Sorry, that's not right. The junction is equal to these 6 variables here. Actually, there's did I get enough of them?
Yeah. Yeah, I mean,
I think I did.
yeah.
Okay, but we have some equations. We have some, these are all going to be, again, variables, and they're all variables in, this is not the set of these things, but these are actually now interpreted as functions into R to R. There's a bunch of them, so 6 of them, right? Into R to R. But we also have some extra thing here, right? Which was that if we take maybe I should I think I need really that I really should have said this was 2 junctions here, J6 and J7. Excuse me. That's going to be better. And then we have this relation J6 plus J7 equals 0. That's better. Okay. And then we have 2 functions like this, which are given by looking at these spans and restricting along them. So I have J7 over here. Yeah, that is going to be better, because this way we can actually have these relations actually can have something to talk about. That's appropriate. Okay. So we have all these ones, and now when I say that we look at these relations, right? What I'm saying is, for example, if we go J1 is going to map to down here. It's going to map to P11. If I'm looking at this diagram, J1 goes to P11. Zoom out a little bit. Right? J2 goes to F11. And then J3, right? Well, sorry, I should say this. It's not. This is a big family here of, as I said before, it's the I1 times I2 is all of these things. Excuse me. Right? So when I take such a map, such a function like this, what I'm doing is I have to set each of these in terms of these variables. So this function here is going to be J1, comma, J3. Did I do? I already did that wrong. It's F. The first one is F1. So I'm just looking at the picture. It's F11 gets J2. F12 gets J6. P11 gets J1. P12 gets J2. So I'm saying that because here, right? P1 F11 gets J2, P11 gets J1, and so on. What did I mess up?
P12 gets J3, I think.
It's J3. J3. And then over here, F21 is J6 again. Is that right? That seems, did I double count that?
F21 is J7.
J7, thank you. And then F22,
J5.
P21 is J3. Note that J3 was duplicated here. And P22 is J4. Right? So, okay, that was a bit annoying, but the point is it's entirely mechanical, right? Really, if you think of these sets of variables as the things that map into R, we're precomposing by these functions. And that ends up selecting out, we take the J1th component of here, we take the J1th component of here, and we send it to, and we set the components of this according to those by precomposition. So this is a formal duality. We took this co-span of finite sets together with this extra little equation here, and we projected it out down here. Now, the act of forming the combined system is given by taking the pullback here categorically. So what is the pullback? Well, it's pairs of all these things. The elements of that pullback, formally speaking, are pairs of elements of here together with elements of here. Now, which subject to the equation that they equal down in here. Now that is a bit of overkill, right? Because we end up with all of the things in here and all of the things in here, but we said a lot of equations are just set by this function here. In the end, what is really important to note is that we have that J6 and J7 pick up this equation here. They get set according to the appropriate flows, F12 and F21, right? That come from here. And they pick up this extra equation here because we have that whatever J6 was in here, it has all of these variables and all of these variables, which include the two H's, right? Which are they're written over here. But we set them equal to by this function. So we set this F11 equal to this J2. So we don't need to have two of them around. We can cancel it out. In the end, you just end up adding this thing. And because the J3s were duplicated, you've ended up setting equal the P12 and the P21. This is a sort of long-winded translation into into the categorical language. But the main thing to note right here is that what we've done is we've taken this pullback over here. And then we can now say, like, what are the new exposed things? Well, the new exposed things are whatever is left out here. And that is given by this projection here, which I didn't write down, but we do the same thing we did over here, where we just look at each one of these and we say, which one did it get set from, to say which component here gets set from which component up here. And so the resulting composite system, which I'll say, if this whole thing was W, right? This thing here is S1, S2 dot W with this relation to the interface I3, the composite. So knowing a bit of category theory, we've seen span double categories before. We can rearrange this, and so we can say, like, knowing about the double category span set, right? So remember, span set, its objects are sets, and its loose morphisms are spans, and the composite of two spans is given by taking pullback. So one thing I can say is that a Jan-Willem system, or a behavioral system, I'll probably call them behavioral, a behavioral system is equivalently, well, it's almost a span, it's like half of a span, right? I could just put in the terminal object over here. There's the terminal object, which is a one element set. It has a unique function for any other set, so I'm not adding any data. I'm just sort of saying, like, yeah, okay, I'm going to make this into a span by adding some trivial data. So is equivalently S, I'll say, in span set 1 I. Right? And a coupling law at its most general, right, is a span, well, W in span set I1 times dot 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 times IN into I prime, let's say. So you can see W here is in I1, I2 to I3. It's a span. That span is J with the left leg and right leg. Right? And the coupling is given by composition in span set. Because composition in span set is given by pullback, right? So we have S1 times dot 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 times Sn. And then I like to use this symbol for pullback. It's like a times, but we've connected the bottom because it's like a product, but we connected the two at the bottom of the leg. W, like this. So yes, this was a kind of a huge believer undertaking to reinterpret adding a few extra equations to a bunch of variables. But now we also see that we get a nice like algebra for the composition of all these things, because we know what this is. We know this double category span set. And now what we're seeing is that so as a result, so we have the behavioral module of systems, which is span set 1 comma dash acted on by span set. And when I say acted on, remember, like, so the idea is that we had these, I think I drew them in green in the last lecture. We had these systems here, and then we had these interactions here, right? But now, in our case, this is going to be a span. And this is another span here. And the composite here is given by the pullback. All right. So this is the first pass at the behavioral approach. But one thing to note is that if I make this definition in general, we lose something kind of important that was implicit in all of this, or not. I mean, I was saying it all the time, and it was kind of annoying that I had to say it all the time, which is that every time I did this, I had this R in the back. Like everything here depended on time. So yes, we could define a system to just be a set of behaviors and exposing some of those behaviors, and then we compose them like by setting things equal. By the way, if we think of this as this is here exposed variables, then taking this pullback, this is variable sharing. In other words, we have multiple different systems, but they can share some of their variables, right? The ones that, at least the ones that we've exposed. Right. So instead of having to say like, okay, well, every single element of these sets varies in time, we could instead bake time variation into the category of sets, right? What I mean by that is it's because the construction only depended on the formation of pullbacks, we could actually replace this by any category. With pullbacks. Any category with pullbacks, you can write down the same sort of thing. And so in particular, what we're going to look at is we're going to look at some nice categories of time varying sets, e.g. time varying sets. And this is a vague notion, and we'll see later on today that you can find what you can be inspired as to what time should mean here by the particular systems theory that you're interested in studying the behaviors of. But there's a bit of a road to get there. So I'm just going to give you an example of what time varying sets could be. The above was continuous, but it's going to be easier if we do discrete time. So let me give an example. So discrete time varying sets. So what do I mean by like a set that varies in time? We'll take Levere calls sheaves variable sets. And the sheaf is a special kind of functor, which is a variant functor into set, plus so-called gluing condition. And we're going to just do discrete time, and this will let us avoid any gluing condition for now. And so what we're going to define is we're going to say that essentially, basically, so for us, a time varying set will be a sheaf. Maybe I'll say this is not quite. Let me move this down here, and we'll see idea of time varying sets. Time varying sets will be a sheaf on a category C, and what could we call the category C? I like to call that the object of we'll call clocks, but you might also call them timelines. So with that in mind, I'm going to talk about the discrete time varying set and its timelines. So discrete time here, by a discrete time is going to be an interval of individual steps that are taken, like tick, 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 like and with nothing in between. So the definition for C, discrete time will be this category, right? So a timeline in discrete time, the only thing you need to know is how many ticks have occurred. So the objects are n in the natural numbers. And we think of an object as, in the timeline, so many ticks have occurred. And then a morphism here will be, by the way, oh, I should say this. This is n plus 1. So this is 0, 1, 2, 3, 4, 5. So this is corresponding to n. To be clear, 0 is no time intervals, I guess you could say, have occurred. It's how many ticks since you started. So no tick at the beginning. All right. So a morphism of time intervals is going to be a subinterval. So n to m is its subinterval inclusion. So an example of this would be like, if I take this subinterval here, so this would be 0, 1, 2, right? I have to label it like that, but I can include it in like this, and it has to be time preserving. So you can see that such an interval is determined by where it starts. So an interval like this is going to be a k such that n plus k is less than or equal to m. That's because if we set k to be too high, the lower one, the smaller one, which was m here, would spill over the edge, and it has to be a subinterval. So there's a few different, if you're a category theorist, there's a few different common ways you might have seen this category before. So one thing I'll say is that this is equivalent to, I can't help myself, the twisted arrow category of the delooping of the natural numbers with plus and 0, the monoid. What does that mean? Well, this thing is the category with a single object, and its loops are n, so its morphisms are n, and a pair of morphisms compose by adding. The identity of this category is 0. The twisted arrow category construction, its objects are arrows in a category, in this case they're natural numbers. And its morphisms are twisted arrows, so are twisted squares. So pairs, k, m, and k prime, such that this composite equals m. So i.e. m is equal to k plus n plus k prime. And as you can see, k prime is, of course, then it must be m minus k plus n. Sorry, m minus k plus n. And so this is the same thing as just giving k. It's determined by k. The other one is you can compute from it. All right, so that's fun. Another thing is that it is what you would call delta inert if you are a simplicial-minded person. The simplicial category is the category of finite non-empty ordinals. And the ordinal here is a strictly ordered linear arrangement. Like that's a great definition for the number of times you have, times steps you have, right? And the inert maps are, so a map in delta, the full category, is a order preserving function. And that is certainly, our maps are certainly order preserving, right? But they're also distance preserving, right? Because if you were just looking at an order preserving one, you could maybe send this one instead to 4. That's still order preserving, but we don't want that because that changes the amount of time that step took, which sort of changes the meaning of what's going on. That would allow you to say, have multiple, you would take 2 steps and turn it into a 1 step. So it changes the notion of time here. Yeah, of course. Yeah, well, yeah, we might return to that idea later. But because boy, yeah, turning 2 things into 1 thing is like the core of category theory. That's what we love. 2 linearly arranged things into 1 linearly arranged thing. It's like all we do. Okay, so the inerts are the order and distance preserving maps between ordinals. And again, it's things of that picture that I wrote above. So you may have seen that before. If you're a kind of homotopically minded person, this will maybe yeah, inspire you. So okay. So when I say sheaves on this, I mean pre-sheaves on this because I'm not going to put a topology on it. So a discrete time. How do I spell discrete? A discrete time temporal set is a pre-sheaf on this category, which I will just call delta inert because it's a pretty short name. So, i.e., it is something x which goes from delta inert up into set. So let's think about what that means, right? i.e., we have for any n, we get something called xn. And it's a generally good idea to think of pre-sheaves. Any pre-sheaf you can always think of as formal functions from the objects of the site, and the site is the thing you're a pre-sheaf on. It's a good idea to think of that. That's validated by the Yoneda lemma, right? Where any element of the like in the value of a pre-sheaf at a certain object is given by an actual morphism of pre-sheaves from the representable in the site. So it's very reasonable to think of this as a function. So we should think of this as functions from this timeline and many times into X, i.e., we'll think of this as n step behaviors. We've taken n steps. And then we have that for any, maybe I'll call it I, from n to m, right? We get a function from m to n, which we can always think of as precompose, right? So take the function x, which goes from this many things, n into x, and we restrict it, and then we take our sub thing here. This is I, this is m, and we restrict it along that inclusion. That's what we're going to think about this as. Okay, so the idea is that we can think of, one way to think of this is that xn is the set of movie reels of length n, you know, this like, yay, whee. Okay, anyway, movie reels, and then you can snip out a movie reel into a smaller movie reel of length m, where this is the inclusion here, I. This would be x restricted along I. That's what I really should say, because it's not x restricted to m, because of course there's multiple different m length segments potentially. Okay, so let's see. So now let's see some examples of where we would get some of these. Like, why do so? My claim is that so one thing I'll say is that set to the delta inert op has pullbacks. Any pre-sheaf category has pullbacks, and the pullbacks are computed pointwise, which means we just do it for all n at that time. Maybe I should say what a map is of these things before we do that. So oh boy. So a map x to y of temporal sets is a natural transformation. So what does that mean? Well, it means that we have functions fn from xn to yn, and then if we select out subcomponents here, so this is restricting along I, this is also restricting along I, this is fn, this is fm, then this has to commute. In other words, the functions are allowed to, they are functions of these movie reels, but if you select out a portion of the movie reel, you have to act in the same way by the function of that length. So one thing to think about is these functions sort of, in a sense, they feel like they are determined by what they do on each frame. That would be true if xn were in fact a sequence of n length frames, right? Okay. I should note that we also, by the way, we have we have x0 here, which can have data, right? So like if you think about it, these frames they might have they have to line up in x0. Okay. Okay. So it has pullbacks. So we get a behavioral module of systems in discrete time, which is, again, it's span now of this thing. This is why doing that translation above is useful, because now we just get to write this and we know it's going to work the same way and handle all this temporality for us. Acted on by span set delta op inert. Okay, so let me give you an example of where we might get this, right? So suppose we have, let's say, suppose we have a labeled transition system G with labels in L. Right? And let's just say that these are edge labels. So let me define for you a system. Remember, a system is still going to be a map like this, but now these are going to be discrete time temporal sets, right? So let me describe I. I is going to be L star, the sequence of labels. Okay, and then S is going to be, I should say this, L star, sequence of labels, I should really say L star N is equal to Ln. Right? As in, by L star, I don't mean the single set of all lists. What I mean is the discrete time set, temporal set, whose n-length sequences are sequences of labels of length n. And for which I need to tell you, how do I restrict? Right? Well, I select out part of that sequence, right? Okay. And then for Sn, I'm going to take paths in G. And again, paths in G is again going to be one of these sets where this is paths of length n. And then this map is going to be the labeling map. Right? So now, right, you can think about this. This is a reasonable notion of behavior in discrete time for a label transition system. Because what is the behavior of a label transition system? Well, you look at your label and you transition. So our interface here is the label that we're making the transition, and the path that sits like one thing I urge to think about is to think about this as a sort of this depends on an element here. So we start with for example, a sequence of labels W, and then over it we get the set of all paths labeled by W. And that is the appropriate notion of trace of such a system or behavior of such a system. Okay. So we might couple this to something that we imagine is generating certain ones of these, right? And what would that do? Well, we would be selecting from the set of labels the ones that are generated by that process. And that selecting from a set is given by a pullback. Right? So that would be a form of composition here. So one thing you may note right here is that we can construct these sets here can be constructed in a pretty cool way like this. Ln, right? Remember that L star, let's look into this. L star of n, right, is defined equal to be Ln. And this is, by definition, the set of functions from sets Ln, well, the n, sorry, I'll say brackets n, n to L, right? Yeah. So this is now, remember that also if we had the, L star of I, M goes like this. This was supposed to be some projections, right? Onto some middle segment, right? Some segment in N. Well, that projection should be given by some map here, which I'll also call I here, into L, restriction along some map here. And what is that map? Well, if I have my segment here, right? So if I have N, right? And then I have M, right? And this is I. So in other words, I is the number 1, M is 2, and M is 5, right? Then the corresponding map, right, is actually given by, well, let's look at this. This is a length of 5 length words. So we're thinking of the labeling here we can think of as having, you know, L1, L2, L3, L4, and L5, right? We're thinking of this as a sequence of jumps, and those jumps happen in these middle pieces here, right? And so this one is supposed to be L2 and L3. Note that we could define a functor from delta inert to set, which maybe I'll put an underbar just to have a name for this functor, underbar, right? Where we send n maps to n underbar, which is the set on that many things, and which sends every inclusion I to the inclusion here, which sends, well, what is this? This is going to be the set 1 dot 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 n, and this is going to be the set 1 dot 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 m. Note that the cuts are the set from 0 to n, but we're doing 1 to n. And what is it? Well, it's just I. It's just going to be I. This goes to like x maps to x plus I. Cool. Note that 0, by the way, gets sent to the empty set. And that's okay. Okay. So let's see how this works. Remember that we have this functor set blank blank, right? From set op times set to set. This is a functor in 2 variables, right? Well, first of all, we filled in one of the variables. So we get set blank comma this goes from set op, and then we filled in that variable. So it goes from set op to set. It's a contravariant functor. And then what we did was we filled that in. So maybe we filled that hole in by this underline function, although opt. Right? So the total thing goes n and underline set, underline, blank underline into L. And this whole thing here is then L star. Of course, we didn't have to plug in from L. We could remain with this bifunctoriality and see that we get this functor at. So, by the way, this is the point is that this is a presheet now. It's a functor on an operator. So we get this whole thing here, which is here, which is which I'll call like blank star, and it's functorial. Why? Because, well, we have this other functoriality in L. So this thing, this process, right, where you take a functor underscore here from delta inert into set, and you produce a functor by mapping out of it, is a very common process. This is called a nerve, the nerve of this. Why is it called a nerve? It's because this was originally done in algebraic topology, and it's a generalization of Alexandrov's nerve of a simplicial complex. You see, we're actually doing a simplicial kind of thing here, but every time you do this, it has been generalized to death, and now it's just called the nerve. So, okay, so L star was formed by a nerve, but we also had path G. Remember, path Gn was defined to be paths of length n in G. Now, I believe we covered this before, but a path of length n in G is a homomorphism of graphs, right? from a path, a graph that's very simple like this into G, where this has n many steps. Right? Well, what do you know? That looks like a nerve again, because we have a sort of obvious functor. You could even define delta inert this way into graphs, where remember n here, remember we were thinking of it as this subdivided interval. And what we're going to do is we're going to take those clicks and we're going to turn them into dots and turn those segments into arrows. 3, 4. And that's going to be our operation, right? Again, this is actually a pretty easy graph to define, right? Because as this is 0, 1, 2, 3, 4. This is 1, 2, 3, 4. So it is the objects here are going to be n plus 1. The edges are going to be n, and we have n plus 1. And this one is going to be, the source of it is going to be the usual inclusion, and the target of it is going to be plus 1. So there's our actual definition of the graph with source and target. And this is sort of evidently functorial, I say. Why? Because, well, if I have a subsegment here, you can verify this yourself using the formal definition, but if I have a subsegment, then I can just map this in, and of course it preserves the edge adjacency relation, because we asked that the subsegment preserves the distance between clicks. Okay, so we get the nerve, which gives us graph to, it always goes into set to the end. This is called path. Which is, of course, defined by path blank is defined equal to be, if I call this, this is the, let me call this P, right? This is defined equal to be graph of P blank blank. Or maybe I'll put a plus in here. So this is the covariant coordinate, and the other one's a contravariant coordinate. That sort of keeps clear which one's which. All right. So, also the map that we got here, where were we? This map that actually exposed the interface of this system, right? The labeling map. What did that mean by that? Well, a path has a sequence of labels, right? But remember, our labeled graph. So one thing I'll note is, first of all, like L star is also equal to path of BL, where this is the one node. This is a graph like this. So one node, and it has loops for every element of L. So, so in other words, we have this labeling map G to L, or to BL, I should say, called L. And what we've done is we've just applied path to it. And path was actually maps out of a certain graph. In fact, you could say it is a map out of a kind of labeled graph if you allow your notion of labeling to also vary. But it's a sort of trivially a self-labeled graph. Right. Okay. So this is a fun way. So another thing I'll note, by the way. Okay, this is our first seeing is that we can construct these systems by mapping out of other systems. I think I'm going to take a little break here, and we'll come and we'll see how we can get these from systems of more machine type.
Okay, sorry, I wanted to start with a question. So before you were talking about spans of sets as being these composition laws, but we only looked at certain spans of Rn to the Rs of a constructed in a certain way with these combinatorial diagrams. And now we're looking at spans of presheaps of sets. And the point is that being one of these delta inert presheaps is sort of encoding a notion of sort of evolution of time in these sets. And of course, is the idea then that your spans of sets are now forced to sort of respect this restriction to sub-time intervals.
Yes, that's exactly right. And I think it may become clearer if I actually go through and see how we build these behavioral systems from discrete time Moore machines.
Right.
So let me just take so the discrete time, discrete space, deterministic Moore machines, also known as Moore machines. So recall that these were lenses of this sort in the tangency, which was the set semi-direct sporadic set over set, with the section being S maps to SS, or I remember that this was the product projections, the objects and the categories were so that, right? And so consider such a thing. Now I'm going to take this and I'm going to define, I'll call it UE, and I'm going to define this to be the behaviors of UE over the behaviors of IO. Let's call it like this. Not a lens. And this will be taking place here. This will be all taking place in set delta inert up. So now we're going to actually get to a system thing. It's going to actually look more like this. So what are the behaviors of the interface? So if I was doing this in set, right, I would say maybe that the behaviors of the interface would be the functions of time in the interface. But now I can say that BIO, right? If it was in set, I might say that it's the set of all I in I to the n, I to the blackboard bold n, and O in O to the n, and that's it actually, right? So that would be like what we were doing before. But now that would be in set. But now we're doing it in set to the n. So instead, I can actually index this by n, and then I can get rid of this and actually say that its sequence is labeled by n. And now B divided to the O, the single thing, includes all of these for all n. And sort of we've sort of taken that variation of n and we've factored it out into the notion of set now. We've redefined set to be this time varying set. So now everything we presume has this same variation in the same kind of time. Is that
yeah, right there. So right for here, like R to the n to the R is sort of corresponds here to like list to the n or
yeah,
something. Okay, that's a discrete version. Okay.
Yeah. So this is what it will be. So that, by the way, equals I to the n times O to the n, right? And over here we have B U E, and it's going to be, well, it's going to be this I in I to the n, O in O to the n, and S in S to the n. But it's going to be subject to certain relations. And that relation is going to be that, well, that E of S, let me say SI is equal to OI, right? And that U of SI at II, oh boy. Crap. Let me call it T because it's time actually. STOT, STIT is equal to ST plus 1, right? So these are trajectories of this system, sequences of states that evolve according to the law of the update process that's given by the system, right? And I'll note that this is bijective with, because this second equation sort of lets me sort of contract out this O, I can say like, actually, I don't need to keep track of the O because it's a functionally determined by the S. I could say that this is actually just I and I to the N, S and S to the N, such that view ST IT is equal to ST plus 1. And that is very kind of clearly a sequence of trace of this system. And this function here is the projection. In the first formula, in the second one, I have to actually apply the E function, I suppose. Right? And so again, when we think of it like this, it's like for all n we have this, but again, we've bundled it up into a single map. So we're just keeping track of that variation of time sort of implicitly once we work here. Okay. So now I want to talk a little about what happens when we share, what happens when we couple. So shall we do a simple example? Let's do a simple example of sequential composition of systems. Just call these A, B, and C right here, right? So this thing, right? Let's look into what that is, right? We have S1 into, it takes in an A, sorry. Takes in an A and it gives out a B. We have S2, which takes in a B and gives out a C. And then we have, when we tensor them together, we get this thing. And then we have here something that takes in an A and gets a C. And this one here is going to be the function that takes B and a C and just projects the C. And this one in here is going to be the function that takes in a B, a C, and an A. And it's going to give me an A and a B. Right? This is what this diagram says. We covered this a few lectures ago. And so so this is what we have here. So now we can turn these all into our span. So here we're going to take this is U1, E1, U2, E2. So here we have BU1, E1, BU2, E2. We have B, A, B, 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 C, both of those maps. And now out here we have B, A, C. And let's see if we can turn this thing, which I'll call W, BW, into something up here that gives us a span, which makes sense. So what should BW be? Well, if we look at like if we look in the wiring diagram W, you can see that there are 3 variables involved, A, B's, and C's, right? So it makes sense that this should be A, B, C in A n times B, or like, A to the n times B to the n times C to the n. That's what BW of n will be. Right? And then what are the maps? Well, here, right, note that what is this? Well, it's a pair of A's and B's and B primes and C's, because we took pairs of both of those. And this map will send A, B, C to A, B, B, C. And on the other side, it will send it to, well, this is just a pair of an A and C, A and a C, right? We'll see we'll see how this comes out by abstract nonsense later. But for now, it's sort of clear that this is what we want to happen. And then we can take this pullback up here. And that pullback up there, so this thing, which is BU1, E1 times BU2 E2 acted on by BW, bunch of B's, right? Let's see what that is, right? Well, it's the S1s. Just right. I'm not writing their types anymore because they're clear from context, I think. It's the S1s, a sequence of S1s, a sequence of S2s, right? An A's, a B's, and a C's, right? Such that, well, we have the equations from this. So we know that ES1 is equal to B, right? Right? And US1A is equal to S1 at, well, you know, these have at T's. T plus 1, right? And then we have also the equations for the other one, S2T equals CT. This is U1, this is U2, S2T, BT equals S2T plus 1, right? That's just taking the pairs of a thing, of a bunch, two things in here, right? Which really, by the way, is this here is from here, and this here is from here, and then we took these all from here, but we set them equal down here, right? In other words, really we had S, A, and B prime. And then here we had SC and B, or SAB, and then here we had SC and B prime, and then we set B and B prime equal because they were mapped from here. Okay, but now we can ask a different thing, right? Which is we could put B over U1, E1, U2, E2 dot W, like all the way on the outside, right? Which is this composite. So what is this thing here, right? This is S1 times S2, S1 times S2, like this, AC, where we look at this thing is S1, S2 maps to E, S2, right? And this one here is S1, S2, A maps to U1 of S1A, comma, U2 of S2, E1 of S1. Again, I refer you to the earlier lecture where we worked out how that really works, right? But that's what it is. And so if we take B of those, right, we get this sequence of, you know, S1, S2, A, B, C, such that, or sorry, AC, excuse me. There's no C, there's no B anymore in this one, right? Such that U1 of S1 at T AT is equal to S1 at T plus 1, and U2 of S2, and now here we have, it's E1 of S1 of T equals S2 T plus 1, and then also E2 of C equals E2, right? dt equals E2 of S2T, right? And the thing I want you to note is that these are bijective, because B here is functionally determined by S1. Like, here's this equation. This is just the exact same thing, but we've substituted that equation in. We've inlined that equation. So there's a canonical bijection here between these two sets. And that is a kind of what we could call compositionality. Right? If you take the composite of the systems and then compute their behaviors, you could have taken the composites of each component and computed a way of some kind of new composition pattern from the composition pattern, and you get and you can take this composition here. And I'll note, by the way, that we took W and we turned it into BW. Now, BW in our other kinds of diagram, right, looks like this, right? Just to say, like, it looks like this, right? And I'll have you note that if you sort of crank the wires on the other one, bend them a little and swivel them around and forget which directionality they had, you can see that those are the same diagram. I mean, they're combinatorially like the same diagram, except that we've forgotten some of the directionality of the other one. Okay? So we're clearly doing something that's sort of procedural here. But so this is where I say, like, it's hopefully it's clear that what we've done is we've taken all these time variations and we've baked them into the background here. Because now what we see is that, I should maybe say that in order for this to be well defined, of course, I have to be able to select out subsequences, right? And they still have to satisfy these laws, and that will be true because these laws are sort of local to one step.
Right. And is that sort of locality, like before you talked about these pre-sheaves on delta inert with the property that xn is determined from all the x1s grouped together over x0s.
Yeah.
As that, and these are all going to be produced by that nerve construction you were talking about.
Yeah. This locality is I suppose that it is true for all of these things. Yes. Yeah.
And does this somehow correspond to like the constraint that these maps between, as opposed to just arbitrary maps between spans of sets, having maps between these particular pre-sheaves are sort of determined by what they do on each time step or something?
Yes. Yes. And so what's actually kind of fun about that is that that actually does give you that gives you a category for each one of these. Like where the objects are the 0 length sequences and the morphisms are the 1 length sequences, and the the morphisms are the n length sequences, I should say, and then the composition is composing sequences. And the fact that these all break down in terms of their 1 length things is what actually makes that still satisfy the axioms of the category. Okay. Right. So clearly we have some way of turning these Moore machines into these behavioral things, right? And what I want to say, right, is that so one thing I'll note is that if you have a discrete time Moore machine like this, in fact, it's not as interesting to do this for the simple reason that if you know the starting state, if it's deterministic and it's discrete, if you know the starting state, you actually know the whole trajectory, and you know the update, you know the whole trajectory, right? So it's not as interesting to do this, but we can do this for different kinds of Moore machines. Like a slightly more interesting version of this is if U here was not in here, but not in this one, but instead we took partial functions. So it's teeny up here, but I'll do this s plus 1. So now U would go from s times I to s plus, let me say, bot, the set containing bot, right? Or it's sometimes known as a maybe monad, maybe s, where the idea is that we have this now we've joined this new like halt state. And this can be a little more interesting. So I'm going to actually work in that setting just so that we have this, because now my claim is that B U E is going to be the maps, Moore machines, right, from some system, some clock of length n into UE. And we're going to get a nerve again, but this time for systems. Okay. So what's my clock? Okay, well, the states of my clock is going to be the set, is going to be this thing. We're going to take, remember n, so n here, we're going to think of as being living in delta inert, right? we're going to think of it as an n transitions. So the states of that will be n plus 1. With n plus 1, n plus 1, also known as brackets n sometimes. It's the same thing. And the interface, I'm just going to reveal the whole thing, and it's going to take no input, which is to say, you can say 1 here. And so this is going to be the id, and I'll write u. What is u? U is a function from n plus 1 times star, which we can just avoid, into m plus 1 plus bot, right? And it's going to be u of I is equal to I plus 1 if, I is less than n, and if I equals n, we're going to halt. So what is the system? It's a discrete time deterministic Moore machine that has n plus 1 states, and it just ticks up every state. And once it's at the end of its length, it halts. This is a perfectly good clock of length n. Remember, I said that we should always think of these temporally varying sets as being things which are formal maps out of sequences of length n. And so in general, when we want to construct constraint ones, it's very often the case that we'll find them to be actual maps out of sequences of length n. And this is a sequence of length n. There's n plus 1 states. We start at 0, but there's n ticks before we halt. Okay. So what is a map here? Remember that a map is a diagram like this. So I'm gonna have to get a little creative here, but it'll help us later. Is a map like this. Now I've usually said that these things are commuting squares, but we'll see that that's actually a little bit annoying in this case. So I'm gonna actually use switcheroo up on you at the end here for real quick to get this to work very nicely. But let's see what this is. Here's my clock. And here is my UE system. So this, of course, breaks down into 2 squares, right? We have n plus 1 into s. So this thing here, right, is going to be SS. So here's our s, or s, in this case, there's s plus bot, because we have the bot back here. This is s plus bot, and this is plus bot. I should have been writing the whole thing. And then here, right, well, this is a pair of maps, which I'll call I and O. And the O is also of this form. This 1, 2, O, O. And I, well, I is of the form m plus 1 times star, which is this thing up here, into I. But that's just another m plus 1. So you see, we have 3 sequences of length m plus 1 here. I think I should have, I think I had an off by 1 error in my above story, but it should be I should have n plus 1 length things, because I want the 0 length things to just be the set of states, roughly speaking, the set of outputs. Okay. And these have to satisfy 2 equations, which we can write out here. So one is that if we have n plus 1 going into s, and then we have this is E clock, the expose of the clock, which is the identity, n plus 1 going to O. Here's E. You can see that this does say that E of S of t equals O of t, which is one of our equations from above. And then the other one is that if we have n plus 1 times star going into n plus 1 plus bot, right, which is tick, our clock tick, U clock, right? And over here, we go into S times I, and this one is S comma I, right? And over here, we go into S plus bot. And here is U. And here we have S plus bot. This equation says that for all t, U of S of t, I of t is equal to S of t plus 1. Or that's if if t is less than n. If t equals n, we actually have that U Sn t In is equal to bot. And that's actually a little annoying because that means that all of our sequences here actually halt at the end. Maybe we don't want that. So if we wanted a looser notion of morphism, we'll see that very often, like one thing I want to say here is that don't be too attached to a particular one of these theories. You want to build the morphism so that they actually represent the behaviors you're actually interested in. So if you built one of these and you get the wrong notion of map, build a new one with a better notion of map. And it's pretty clear that there's an easier notion of map here if we allow ourselves to have a inequality that goes this way. So I will say that like if I take S plus bot, I can have an inequality where bot is less than or equal to S, and then S is less than or equal to S prime if and only if for all S, if and only if S equals S prime. And now I can say here that we know that on if t is less than n, right? Then we have that u s t I t is well, what I've said here is that s t plus 1 is less than or equal to that in that ordering. That's what I've said with when I put this here, I mean that for all, we replace this equality by an inequality going in this direction. So that this is less than or equal to that, like this, which is what I've written down here. But now note that these are both neither of these are well. If S of t plus 1 isn't bot, then this says that they're equal. Right? Unless if we update into halt, in which case we also have to halt. There's only sort of two cases here, right? But if t equals n, right, then we know that this here is bot, and then we want that to be on this side. And that doesn't say anything at all, because we've made this assumption here, or this definition of less than or equal to. So using this notion of morphism, which we could call a collax morphism, yes, it is collax. There's a way to figure out whether something is lax or collax, and this one's collax. I've worked it out once, and that's it. It's a collax morphism. If I had written the structure, when you write the structure vertically, the way to know is if you write the structure going vertically, collax goes up and to the right. If you write it horizontally, it goes down and to the left. That's what collax means. Yeah.
Yeah, for algebras, yeah, but for like transformations, collax ones are the ones that go down.
Oh, brutal.
Anyway, it's a bit confusing.
Okay. Anyway, so this kind of morphism we'll see more. We'll see again because Lyapunov functions, if we ever get there, which we will get there, Lyapunov functions are another example of collax morphisms that are very, very good to know about. So, one thing I'll say is that in non-deterministic kinds of systems, it's often useful to use collax morphisms instead of strict morphisms, because a strict morphism in a non-deterministic setting essentially says that you want all of the image of all the ways you could transition to equal all the ways you could transition in the image. Whereas if you just say that it's collax, what we've said is that the image of all the ways we can transition contains all the ways we can transition. In other words, or is contained in all the ways we can transition, which means it's a valid sequence, but it's not exhaustive, right? So again, it really depends on which system theory you take, which notion of behavior you get, and you should tailor it to your task at hand. But what we've succeeded in doing in giving this notion of morphism here, where I'll stick this in, what we've succeeded in doing in giving this notion of morphism is that, what do you know? We've actually discovered that the sequences here, that this claim is true, but as long as we define this notion of morphism. So maybe I'll use more with collags. Yeah. Okay. And so now one thing I'll have you note is that also with this notion of morphism, any sub-inclusion gives us a morphism of clocks. Therefore, we get a nerve. So again, we get B is equal to more collax from clock, or B of plus, and this goes from more collax to set to inner. Oh boy, that's an error. But it's actually more than that, because this is a thing about functors, about categories, but we're going to actually see that this extends to, in fact, more like this as a module over the wiring diagrams into spans of these things as a module over spans. So we're really going to see that B looks like this. And that's going to explain the formula we saw above, right? So now I can ask you, like, what is B of W? Well, my claim is it's actually going to be just more from clock into W, if we can figure out what that expression means. Right? So now W is something that only took place on the interfaces. So we only actually need to look at the interface of the clock. So here I'm going to write up the interface of the clock. And over here, I'll put W, and I'll just put it like, we'll have IO, and we'll have I prime, O prime, and we'll have just W like this. So W sharp. Feedback, right? And here, I'm actually just going to put equalities. This is going to say the identity on the interface of the clock is what we're going to actually map out on. So now it should actually be here, it's really going to end up being the identity of the interface of the clock, which, by the way, is also functorial in delta inert. It's in fact exactly the forgetful functor to set of delta inert, if you think of it as an ordinal. Okay, so what is a map like this? Let's take a look. A map here, as we saw before, is a sequence of i's and o's. And the map here is a sequence of I primes and O primes, both indexed by n+1. All indexed by n+1. And then, of course, I must put this in because we've decided to do that for systems, and we need these things to be closed under the horizontal composition, which, by the way, I give as an exercise to actually check that this change I made still gives you a double category, which requires you to check a few axioms. Okay. What does this mean? Well, this means two things. One, for all t in n+1, right? So for all t less than or equal to n, from 0 to n, right? We have that W of OT is equal to O prime t. And two, we have that W sharp, or let me make sure that I do this the right way. Yeah, it is W sharp. Well, yeah, W sharp of I prime of T. Sorry, we have this. It's O prime of T. Wow, I missed some of the strokes. O prime of T, I prime of T, right, is less than or equal to, again, in this very simple ordering, which is just that it's equality unless if you're bottom, in which case we allow you to be underneath anything, is less than or equal to I of T. Right? These are just writing out the same sort of formulas that I wrote up above, but now in this case. Okay. Now, if our wiring pattern did not use this indeterminism, then this would be inequality. And I'm just going to write that here. That is fair. Because that's it, when we made our wiring diagrams, there was none of that. There was no partial map anywhere. So if we look at this formula and then we go way back up here to where we did this process where we turned that this picture up there into this BW, and we did that by just sort of looking at what it must be, right? So I'll note that this is here, right? We took A, B's, and C's because we said those are the three wires and that's what the behaviors would look like. But one thing I want to note here is that this is the same thing as this is bijective with. Again, you'll note there's a lot of these, like when you turn it into the category theory, the most direct, the literal translation ends up with a lot more variables that are all then canceled out by a lot of very simple inequalities, nevertheless, right? This is equivalent to saying that we have an A and a B prime and a C, and an A prime and a C prime, all functions all in the appropriate ... to the n+1, it should be. That should have been fixed all the way up, right? Such that, right, as we have here, C prime is equal to C, which, by the way, is, of course, W of A, B, W of all that. If we look at the W that we would get from up here, I don't know if I've written it out, but if you go back a few lectures and see how you do the translation, you'll see it's there. So C prime equals C, right? And then also A prime comma B prime is equal to A comma B, which of course means A prime equals A and B prime equals B. And that does collapse this down into A, B, C. And then if you do that, by the way, these two maps here do not have to do anything. They just project out, right? And that's exactly what we computed as a sort of map like this. And so now what we can note is that if we have one of these things here, right? And then we have our clock system here. Oh, this is a clock. And we have a behavior like this. Then so long as this is still a double category, which I claim it is, and it's not too hard to check, then you see that we could do this, or we could take the composite first and then map out. Because this composite up here is still clock n. That's why we put the identity over there. So given any behavior of the inner one, we get a behavior of the outer one. Now that does not say it's a bijection. That just says that given a behavior of the components and a behavior of the coupling law, we get a behavior of the composite. Let me see this. So the first compositionality, T principle. Oh, is given a behavior of the component systems, and a behavior of the coupling law, by which I mean a square of the above sort, we get a behavior of the composite. So what we can say, right, is that given what does that look like in terms of the above thing? Well, we'll say that given a behavior of the system, right, and the behavior of the component of the coupling law, W, that agree on the interface, right, that makes sense, right? We can get a behavior of the composite. So that's the direction that's natural. That direction is known as lax. Right. Now, we'll note, so it's a fact, and I may come back to give a cleaner analysis of this fact later. But fact, if a Moore machine clock exposes its entire state, i.e. E clock is ISO, which R's above is, we took it to be the identity, then the above will be a bijection. I may at some point turn around to prove this, but I don't think I'm going to do it now. That's the situation we're in. Okay, so this is a first taste of functoriality, and then I think we'll come back and see more of this later. I want to maybe this is a good pause, and then I'll come back and talk about what we can do once we've turned a system into one of these time-varying sets of behaviors.